party rowing. Hello everyone, February 22nd. Lots of twos today. Alright, let's do this. Construct a binary tree from pre-order and post-order traversal. Oh my god, I had a lot of food. That was a good burp. Given two integer arrays, pre-order and post-order. Damn, what's post-order? Pre-order. Wait, hold on. What's pre-order?
I remember that.
Pre-order is. I think I searched for pre-order yesterday. I forgot again. Pre-order is. Node left right. That's pre-order. What's post-order?
Oh, right, left.
Post-order. Left right node. Left right root. Left right root is called post-order. Root left right is called pre-order. I never memorized the two. I don't know. I have to check it every single time. Because to me, it doesn't really matter that much which one is. You just do whatever order you want to do. There's also in order, I remember. That I think that's a left, root, right. That's in order. Pre-order is visit root. Okay, pre-order is visiting the root first. Post-order is visiting the root last. Okay, so binary tree of distinct values. You need to reconstruct the tree. Okay, so if multiple exist, so you just need to find one of them. So pre-order 1, 2, 4, 5, 3, 6, 7. Post order 4, 5, 2, 6. Hold on. 4, 5, 2, 1, 6, 7, 3. Nope. 4, 5, 2, 6, 7, 3, 1. Okay. So, from pre-order, we don't know, right? So pre-order is visit the root first, okay? And then we visit the left, but we don't know where is the left. Post order is to visit left first, so we know the most left. Huh. So in the post order left, right, so you basically go left all the way down, right? That's post order. You go left, 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 left all the way down, and then if there's no more left, you go right down. So the first node will be the bottom, the leftmost. Yeah, how do I reconstruct? Oh. rồi. Maybe. So we start from the root. So that's 1, 2, 4, 5, 3, 6, 7. And the other is 4, 5, 2, 6, 7, 3, 1. So we start from the root. Pre-order will go to the left, right? And the post-order, the last one should be the right. So we compare this and this. Right? If they're the same, that means we have one node, one child. If they're not the same, then this gives us a left, this gives us a right. Now move on. This is also move on. But this move on, that doesn't really say anything because this keep going is going to be its children, and this is going to be its children. Nah, I don't think so. I think given length is 20, I'm actually inclined to do it brute force. We just create, let's say from this, we create whatever tree that we can, and then we'll verify by this. And then we find the first one that matches both. So yeah, we start from root. So the 2, and it can be a left, and it can be a right. Right? We don't know. So we say, okay, let's be a left. Now 4, it can be a left, it can be a right. Right? That's essentially what it is. It's brute force. We'll go through all possibilities. So let's say 4 is a left. Right? Next 5, it can be a left, it can be a right. Let's say 5 is a left. 3 is a left. 6 is a left. 7 is a left. So we produce this. Once we're done, we'll run a post order, and it will produce an array. Then we'll compare to the post order. If it's the same, return true. If it's not, we will return false. So we'll put the last one, on the right is false. Then we'll put this one here, because 3. Basically, I say the next is gonna be 6 is gonna be the left. I say no, 6 is gonna be the left and the right. Okay, and then we go 7 with our left and right, and we try. No, coming back. So yeah, I just keep, and eventually we have 4 is left, is not right. Now we say 5 is gonna go 4, 5 is no good, and then 2 and then go 4. Oh, hold on. So it's actually 3 different ways, because you can go here, or you can put 4 here, or you can get 5 to come here. Yeah, so next can be here 3, right? And then from this perspective, I can do 3, or I can do 6 here, right? Oh, now we have a lot more options. Right, so I'm at my position, then I look my next, I say, okay, you can go to the left, and then I'll keep going, go to the left, then I say, I don't have one left subtree, or I only have one right subtree, or I have, so it's like 3 different options. You have 3 different options. Oh, that's 3 to the power of 30. That just completely changed the game, right? Because you have 1, or this. Oh, that's way too much. Yeah, it's not just 2 to the power. The 2 to the power of 20, probably there's still a way, but no, I don't think so. I don't think that's the way. I think we need to analyze this. But dude, how? So we go with 1, and then basically we have some of them is going to be the left subtree. Some of them belong to the right subtree, right? But we don't know where the boundary is. And here, so we go left first, right. So which means some of this is going to belong to the left, some of them is going to belong to the right. I think we know how to do this. So we know the root, right? And then I just go down. I go here, right? Oh, but how do we match the two? Let me think. Yeah, so it will be like a left subtree and a right subtree, and this will be a left subtree and a right subtree. So I find the first, it basically means there shall be a part, right? If we can find a part starting from the front for the post order to match whatever is here, they will form one subtree, right? They will form one subtree. And this is the root, right? This basically is the root. Because I have the original root, then we have a left subtree root. It's either a left subtree root or the right subtree root. We don't know, depending on how the tree is formed. But it does not matter. What matters is we have this number. This 2 is going to be a subtree root, and I will search through the post order until we find it. And we know in the post order, root is the last one that gets visited, right? Then we have this part, and basically we need to find, how, no, I know, because this is the subtree root, and then we know the length, because that's the whole subtree. Then from here, I just count the same number, and then we're done, right? This is the subtree. And then the remainder is going to be the other subtree. Then we run the same algorithm, right? The same algorithm. So we, here's how I'm going to do it. We identify the root, one's at the front, one's at the end. Perfect. And then I identify the subtree root, and on the other one, I will just do a scan from the start until we find the subtree root. Right? Once I find it, I will run the same on this, right? We run the same on this. And then it's potentially a left child, right? First child. And then we see if there's anything left. If there's anything left, then we do this entire thing, and then this entire thing we do another one. And then we do, now this one become 2, 4, 5 to match with 4, 5, 2. And then I say 2 and 2 is a root. So and then 4 is going to be the sub, right? Then we find 4, right? Then we say this is gonna form a new group. Then we're gonna form 4. So once the start and end is the same, that's just gonna be a root by itself. Oh, got it. Wow, it take a little while, a little bit longer than I wanted. I had hoped for it to be a little bit simpler, but it's not that bad. It's not that bad. I think it's gonna be interesting when we implement it. That's one of the reasons why I like tree, because it's just so much more fun, honestly. Right? It's just so fun. Lots and lots of fun. Can't even imagine. Because once you are able to get the recursion part right, it's just really a lot of fun. All right, so we need another function. Let's call it. Let's do a private tree node. Let's call it build. So we need is the two vectors, sure. Right, we need the two vectors, pre-order, vector, post order. Right, and you know what? Let's do the pi, pj, p low, p high, p low, p high, and then this is going to be, oh, damn it, pre-post, oh, post, pre. Okay, pre-low, pre-high. How about that? It's not any ambiguous. Pulse low and pulse high. There we go. All right, if pre-low equal to pre-high and pulse low equal to pulse high, right? Then we'll return. Right, we'll return new tree node. Alright, if it's not the same, right, then we say tree node root, tree node pre-order, preload. Right, the preload is the root, the post is also the root, and then we need to find, right, say for while no int I equal to post low, while I is smaller equal to post high, and post order I is not equal to pre-order preload plus 1, right? Because preload plus 1 is the new root. Then we do I++, right? We'll do I++, keep going until post order I is equal to pre-order preload plus 1, right? When these two are equal, now we jump out, then I know child, right? So we say tree node star child, but we don't know if it's a left or right child, and we need to build again, pre-order. So here is going to be preload plus 1, right? Preload plus 1 and preload plus 1 and preload plus 1 plus so I is where they equal. So basically I minus post low 0, 1, 2 plus 1 I minus post low plus 1 is the total count. Okay, and then preload plus 1 plus the total count. So I need to not do this minus 1. So yeah, so this is going to be the new pre-high. Preload plus I minus post low plus 1. So I minus post low is the total count. I say 1, 2, 3. Yep. So that's that. And we do post order. Post low. And post high. So post low it do not change. I think it's the same. Post high is going to be I. Right, that's the child. Okay, child 1. And then child 2, right? Tree node child 2 shall equal to build preorder preload plus 1. No, not preload plus 1. And preload plus 1 plus I minus post load plus 1, right? Because that's how I'm going to do that. And then post order I plus 1, right, all the way to post high. I feel like there's another one, right? Which is just if preload is larger or equal to preorder dot size, and yeah, that's basically it, because the post will not get out of bound, because the post is always going to be post high. So preload is larger or equal to this. Huh. Actually, we are wrong. We have not get another one. So the preload plus 1, we get this, right? So plus I minus this. And then the end is always pre-high. Yeah, so the pre-high and that's pre-high never change, right? Post-high also never change. So it's not larger or equal to this. It's more larger than pre-high, or post low larger than post high when this have a return no pointer. Okay, and then once we're done, right, and we say if child 2 is equal to no pointer, so we only have one, child 1, I don't even need this. I can just always put on the left. The left. Say other child. If other child is not equal to then we say root right equal to other child. And now we'll return root. So here we'll just return build, preorder, preload 0, pre-high is preorder dot size. That's one post order 0, post order dot size -1. Alright, let's take a look. Does this work? We have some issue. It's probably preload +1. And preload +1 is smaller equal to pre-high. Okay, let's try it again. The hell is this? What the hell is this? I mean, I already got a 1, 2, 3, 4, 5, 7. I already got everything. What are these? Oh, I find out this should be -1. And no, not here, but here. This should be -1. Because pre-order +1, then we do whatever. Post order and post load to I. Yeah, that's the two we match. And then the remaining, this goes to pre-high, but this goes to post-high -1. Okay, I'll try it again. There we go. That's the answer. I think we should write something for this. Mm. 889. Pre-order 0 and post order -1 must be the same, and the root of the current tree. Pre-order 1 must be the root of a child tree, maybe a left or a right child. Then we traverse post order from the start until we encounter the same value as pre-order 1. Then we have a subarray that represents the entire child tree. We can build the tree using the subarray. Then we can build the other child tree with the remaining subarray, if such a remaining subarray exists. Then we assemble the current tree. Boom. Done. Runtime, we go through every single. We essentially cut them in half. So that's log n, right? But during this, we have to go through them one by one. So I believe we shall call it O log n log n. That's my guess. Because you need to know when does it end. So you just, each time you have to go n. And next time you have to go n. Next time, you have to go n. Yeah, I think it is. O log n. Not very sure, but we'll see. We'll run this again, and looks solid. Maybe you have some other idea. Let me do another one, right? How about we say 1, 2, 3, 4. And then post order will be 4, 3, 2, 1. Just one line. It's a one of them. Okay, let's try it. Yep, looks about right. That was good, and we need to check if the complexity actually submit. Wait, hold a second. Did I click it twice? Submission length exceeds limit. Okay, that's fine. Let's read. Blah blah blah. Construct tree. Pre-order, post order. 2. Oh, they only have 3. Pre-start, pre-end, and a post-start. Pre-start, pre-end, and post-start. It doesn't need a post-end, but I use post-end, right? I use post-high at least. These, yeah, that's okay. Here. Because I need to move forward. I do need post-high though. Because I am going forward. Right? But the maybe it's pre-high. Do we use pre-high? We don't need this, maybe. This, I don't know. This part, I do need both. So we still have slight difference. But overall, I think it's about the same. Start larger than end, start equal to end. So this is just these two, okay? And then left root is this one plus 1. But it did not check for this. I wonder if this is going to give us any trouble. Oh, it will not. Because of this. Right? If plus 1 is larger than... hold a second. So I allow it to equal. Right? Oh, yeah. Yeah, I think I don't need a pre-high. I can take the pre-high out. And the rest, you see the same, post. And this is the position, not equal to left root. That's exactly the same as what we do left plus plus, and then we'll create the root. The left will be construct. The right will be construct. Oh, dude. You don't even need to do this. Ah. Darn. Darn. That's absolutely darn. I think I can even change it this way. Watch. It'll be absolutely bonkers, but it'll work. Look, I set I do this, right? And then I directly return new tree node, pre-order, preload, left, and right. Expected expression, I have no idea. Okay, it required it this way. Right, that's how it's supposed to be. I wonder. I think this will be right as well, but we should try. Even simpler recursion function, recursion implementation. I like to keep them both, right? But now I can see I don't need pre, right? I don't need pre, so I can just delete this. I don't need pre. I just the post, right? I just do post. Actually, I'm not sure. Yeah, I'm not sure. What if pre low plus one gets too much, too large? You know what? Screw that. I'll keep everybody. Oh, how? That was exactly the same implementation. Nah, doesn't matter. O(n) squared. I thought it's O(n) log n. Really? We call a function n times. I don't think so. How would you call the function n times? Because you run this, that's on, I agree. And then you call this, you call the first half, and then you call the second half, right? You call the first half, which does just go down one, but you basically get this part and this part. You call that, and you call the other half, and each half you break it out into two. You break out into two, you break out into two. Well, you do. You only do log n if one half you don't handle. Yeah, now I remember. Because you have to go to both halves, so yeah, it's O n squared. I agree. Indexing. I did index. Smart. Yep. Because that's exactly what we want. We just need an index. Holy crap. Yeah, you just need an index. Then you can save this. You can save this. Everything else is the same. Optimize the recursion. Hmm. If the root is not the last of its subtree. If the root is not the last of its subtree. What if the root is the last of the subtree? So basically the two pointed to the same. Oh, root dot vowel. Okay. Okay, yep. If root dot vowel is not equal to, I get it. If the root dot vowel is not equal to the post order, then you are not at the leaf. Then you just call the left, you construct a tree on that one. So you just keep doing it until you hit the node, right? So you just keep going until you hit the node that's the same. Then you know you cannot hit anymore, right? You cannot hit anymore, and then post order will move forward because this one you basically hit everything on the left side. Yeah, you hit everything on the left side, then you go up. Then you hit the right side, and the first time. Then you hit, okay, and then so move on, right? And then I go back up. And then it becomes the same again. Then we'll back up again. Holy crap. Wow, this is the ultimate solution. Yeah, we have the root. Mark the current as created. Recursive construct the left side of the subtree. As long as the root value is not the last on the post order. Because the post order we have a pointer, right? So as long as we don't hit the last, because post order we go left first, right? So we hit this, and that's it. We hit the end of, then we go back up. Then the post order we use this. Then we need to go to the next one on the post order. All right, and then on the pre-order we have finished the left. We're gonna go to the right, right? So go to the right. Then we again keep going left, right? We go to the right, and then we keep going left until we hit post order. We hit whatever it is. Then we go back up, right? Then we just always move forward and go back up, and then we will do. Yeah, just keep going the same. Now we keep going the same, and once I hit both sides, if a subtree is done, then we just go back up. I don't think I'll be able to get this. I think if you ask me to solve it again, I'll probably give you this solution again. But the indexed will definitely make it faster. But this is definitely the ultimate solution. Alright, that'll be it. It is a good problem. Alright, I'll see you guys tomorrow. Adios.